All right, hi guys, back again for a merit question a day. We're going to do 3 different merit questions within this one video, one for each of the 3 standards that are coming up for level 3 calculus. We'll do complex numbers, then differentiation, then integration. Each of these are from papers from quite a while back. I'm actually using some from 2013 today, just because it means it's going to be questions you probably haven't seen recently, but they are very much in the same style. These standards have not changed a lot in the years in between, so they're still very, very helpful. Okay, so I will try and do a little better at keeping an eye on the live stream itself today. I missed a question right at the end yesterday. I kind of hadn't noticed that there was a bit of a delay, but yeah, I'll see if I can do a bit better. If anybody does have questions, I'll try and keep an eye on that in the corner. Okay, so, and I'll be looking down a fair bit. I'm needing to use a home setup today, so I don't have a second screen to do this on. Okay, so let's go with this complex numbers question first of all. So we have this setup with z is 1 plus I, and w is 1 over z plus I. Okay, so what we're going to do with that is work out the w equals 1 over z plus I first. So this is the same as if we were to put z in like this. So that's 1 over 1 plus I plus I. Now I'm going to use the calculator to do this. Just save us a little bit of time. So we'll do 1 divided by 1 plus... Oh, hang on. What I'll do is I'll use the cursor so you can see what I'm doing. So 1 divided by 1 plus I, and then that comes to this, and then if we add another I on to finish off what we had in our working out, that's going to be 0.5 plus 0.5 I. Now we're asked to find the argument of W, so the argument means the angle that it makes from the positive section of the x-axis. So it's this bit just here. So let's plot this. We've got 0.5, 0.5, which means that it's going the same in the x as it is in the y. So it's 0.5 along and 0.5 up. That means we get a isosceles triangle. Sorry, just one moment. Bear with me. Okay, so we have the same length on either one of those sides, which means that this just here is 45 degrees, or pi by 4. So the argument of W is equal to pi by 4. And because it's in this top right quadrant, it's a positive pi by 4, because we're going around in that direction. If we'd ended up below, for example, it would have been a negative that we'd put in our argument. But this one is just a pi by 4. I think that's a really lovely, straightforward merit question. If you get one like that in the exam, then that's a real gift. So the achieved was for getting to this point here. So working out, well, subbing it in and working out what that would be. And then the merit for actually finishing it off. All right, so that takes us on to our next one, differentiation. This one we've got parametric equations. So a curve is defined by these parametric equations. We've got x and y separated. To do parametric equations, we do each one separately. So differentiate x with respect to t. Now sine becomes cos. The 5 in front of it is just being multiplied by the whole lot. So that doesn't change the derivative itself. Then dy by dt is the derivative of tan. Now tan differentiates to sec squared. This is all on your formula sheet. Even I don't memorize all of these ones. I just can't hold them in my brain. So I always look them up on a formula sheet. So tan goes to sec squared. So this will be 3 sec squared of t. Now this is probably going to be helpful to write this out as what sec squared is. So sec is 1 over cos. So this is 3 over cos squared t. The reason I've done this is because we're going to be multiplying these things together, so it's helpful to be able to know the tops and the bottoms of your fractions. So dy by dx is dy by dt multiplied by dt by dx. So that dt by dx is this bit flipped over, because this was dx by dt, we want it the other way up. So we have dy by dt, 3 over cos squared t, multiplied by 1 over 5 cos t. So that's 3 over 5 cos cubed t. Now we're doing this where t is equal to pi by 3. So if we set t is equal to pi by 3, then let me just grab my calculator. Sorry, just one moment. Oh yeah, that's still there. Okay, so if we've got on the calculator, we pop in cos of pi by 3. That's equal to 1/2. Now do that to a cube. So what I'm doing here is when t is pi by 3, dy by dx will be 3 over 5 times, this will be 1/2 cubed, because cos of pi by 3 is 1/2. I'll just pop that to the side. Okay. So if we carry on working that through, let me just go back over to here. We're going to do, that one gets times by 5, then we'll do 3 divided by our answer, and we get 4.8. Now, since I'm going to do the negative reciprocal, I'm going to actually turn that into a fraction. Just, I prefer to think of it that way around, but you can still carry on in decimals. So then that was the gradient of the tangent. So the gradient of the normal, which was asked for in the question, is the negative reciprocal of that. So we make it minus and we flip it over. Okay, now on this one, the achieved was for getting to this line here. So you had a fairly straightforward achieved point within there. So getting the dy by dt and the dx by dt values. And then merit getting all the way to the end for gradient of the normal. Okay. All right, so on to integration. Okay. All right, so we're going to use integration to find the area enclosed between these two graphs. What we need first of all is where those graphs intersect. Okay, so if we set them to, so the y values are equal to each other, I'm actually just going to write this out again so I can see them a little more clearly. So, that's an x. If we were to do something to set them equal to each other, I'm going to turn this into 3y equals 6x. So then I can say x squared is equal to 6x and solve this. So x minus 6. And remember, we always need to factorize to do these sorts of solving so that we don't lose any solutions. So x is 0 or x is 6. So we're going to be integrating between 0 and 6. That's where those two curves cross over. I'm also going to write this one as a third x squared so we can picture what this looks like. So sometimes it can help you to draw a little sketch in your mind so you know what you're talking about. So y equals 2x is a straight line like this, and y equals a third of x is going to be a parabola, something like this. In fact, I think it's going to sit more like underneath like that. Yep, there we go, because then we've got our 2 points of intersection. Okay. So now we're integrating to find the area between them, just here. So we'll do that between 0 and 6. And we need to do the top line here. We can tell from our sketch is going to be 2x. Now, if you get these the wrong way round, it's not too big of a deal, because at the end you'll just get a negative instead of the positive area answer you were looking for. So if you do end up with a negative at the end, you know you've just switched those two things around at the beginning, and you can go back and fix that up. But it's helpful from the start. If we can picture what that looks like this one, then we can tell the straight line is the one that's on the top, and we're going to take away the curved line that's underneath it. So y equals 2x, take away y equals a third of x squared. And we're integrating that with respect to x. There we go. So this becomes, well, 2x becomes x squared and then divided by 2, so the 2's will cancel. And then the x squared is increased by 1, so that's x cubed, and divide by the 3. We already had a 3 at the bottom, so now we've got it over 9. Between 6 and 0. So now we substitute in the 6, like so. And we'll take away, if we sub in the 0, we get 0 minus 0 like this. So then we'll just pop that in, 6 squared minus 6 cubed, oops, that was supposed to be a 6 cubed divided by 9 equals 12. And I always like to finish this by saying it's 12 units squared. Whatever units we were measuring in would have got squared. It's not entirely necessary though. All right, so for the achieved point in there, it would be getting you down to the correct integration. I'm just going to double check. I'm assuming that's what it would be. Yeah, so the correct integral was where the achieved point was. So this bit just here, that's your achieved. And then obviously getting to the 12 gets you the merit. So there we have it. We've done it in less than 15 minutes, got a merit question from each of those 3 papers. Now in the real external, that would mean that you are a third of the way to getting a merit on all 3 papers within a 3-hour exam. So this is totally doable. You need 1 merit question on each of those 3 papers correct to get your 5 points on that paper. Okay, now I noticed last time I think I shut down the live stream just a fraction too early, just because of the little bit of delay between me doing it and it ending up on the live stream. So I'll just give this a minute and then I will shut down the live stream. So any urgent questions can pop up in the side and I will hop on and answer them.